Today we'll discuss about session 23 called as black body radiation. So in this session we'll deals about some black body radiation, what are the assumptions of black body radiation, and we'll discuss about energy distribution of black body radiation. Now, to understand black body radiation and energy distribution of energy of black body radiations. Now, this is defined black body radiation and black body radiation laws called as Planck's law, Wien's displacement law, and Stephens Boltzmann law and Rayleigh-Jeans law, and some applications of black body radiation. Now, the black body is an importance in thermal radiation theory and practice. The ideal black body notation is importance in studying thermal and radiation and electromagnetic radiation transfer in all wavelength bands. The black body is used as a standard with the absorption of real bodies is compared. So, what is the definition of black body? A black body is an ideal body which allows the whole of the incident radiation to pass into itself without reflecting the energy and absorbs within itself this whole incidence in radiation without passing the energy. This property valid for the radiation corresponding to all wavelengths and to all angles of incidence. Therefore, black body is an ideal absorber of incident radiation. Now, the black body radiation laws, first law is called as Rayleigh-Jeans law, that is intensity absorbed by the black body radiation is equal to 2 pi c kt divided by lambda to the power of 4. It agrees with an experimental measurements for long wavelengths. It predicts an energy output that derives uh, towards as infinity as wavelength grows smaller. The failure has become known as ultraviolet catastrophe. So this formula is also had a problem. The problem was the term called as wavelength in denominator. For longer wavelength, it fitted with an experimental data, but major problem at shorter wavelengths. As shown in figure, the short wavelengths as shown is in experimental graphs. So next one is called as Planck's law. There are two waveforms. One it is in terms of wavelength, another one in terms of frequency. Planck's law gives a distribution that peaks at different wavelengths. The peaks shift towards shorter wavelengths for higher temperatures, and the area under the curve grows rapidly with increase in temperature. Then another law is called as Wien's displacement law. It tells us we heat the object up, its color changes from red to orange to white hot. You can see use this to calculate the temperature of the star. The temperature or surface temperature of the sun is 5778 Kelvin. This temperature corresponding to the peak emission 502 nanometer of about 5000 Armstrong. B is called as constant of proportionality and it is called as Wien's displacement constant and it is equal to 2.8977685 in 10 to the power of minus 3 meter, where K is called as 2.8977685 into 10 to the power of 6 nanometer per nanometer Kelvin. Now another law is called as black body radiation and it is called as the total energy emitted is directly proportional to the fourth power of absolute temperature. This gives the total energy being emitted in all wavelengths by the black body which is under the curve of Planck's law curve. It explains the growth in the height of the curve as the temperature increases. Notice that this growth is very abrupt. Sigma is the value 5.67 in 10 to the power of minus 8. It is called as Stephens Boltzmann constant. Thank you.